moment of inertia. And I believe we started last time with this. We had
People use it all the time, so you should go back in time and sue them and use that.
I can't sue them. I can just say
okay, first of all, we talked about center of mass last time.
Yes.
Center of mass, remember, is that location about which a point will balance. If you hang it from some spot and it's free to rotate, then the center of mass will be below that point. So you can take any object and hang it, like get to any random object. And if you hang it by this spot right here, the center of mass will be right below it. And if you hang it by this spot here, then it will hang so the vertical line that it hangs from, I mean, when you hang it and it stops moving, you can draw a vertical line from the pivot point straight down, and you can find the center of mass that way. Or you can balance it at that point. Or you can use math to find it. And what was our equation to find center of mass?
it's like the sum of x m's over m over sum of x.
Okay? Center of mass equals this, or you could say the integral of the x dm's over the integral of the dm's, right?
Yeah.
Either one of those. All right, now that's the center of mass point. If we have an object that has mass, then remember that if we have some strange-shaped object and its center of mass is right here,
Very squeaky markers.
yes, it's a squeaky marker.
It's even louder.
All right, then we will write center of mass, or the weight coming straight down from the center of mass, right?
Yes.
Okay. So there we go. Also, if we take this object and we spin it through the air, we throw it and it's free to rotate with no impedance, no hindrance of any kind, then it will naturally rotate about this point. So you can see that this point is important for people that work at NASA because this is the point about which objects will freely rotate in space.
That's the
Okay.
people.
Yes, like if you take a person and throw them, they will rotate about that point. Yes, ma'am?
Totally off topic, but on the recommendation letter list, are you including the people?
What is wrong with people?
Might as well. Just put them down. So I don't, in case I miss one. All right. Now that's center of mass. But we've got this new thing that we began to talk about last time called I, moment of inertia. Think of it as rotational mass or rotational inertia, okay? It serves the same purpose as M in F equals ma. Now we have torque equals I alpha. It serves the exact same purpose as mass does. The larger the mass of an object is, the more inertia it has, and so therefore the more force is required to make it accelerate. Okay? Same thing is true here. The more moment of inertia an object has, the more torque is required to change its rotational motion. Okay? All right, the difference is that mass is mass is mass. It doesn't matter how the object is shaped. Mass is mass. But for inertia, moment of inertia, where the mass is located makes a difference as to how its rotational inertia what its rotational inertia is going to be. Okay? So, we began, or I guess we ended last time with this equation, which is moment of inertia is the sum of the mr squareds. Okay, you just sum them all up. And if you really want to be technical, you put little i's here. Okay? Or it's the integral of r squared dm. Okay? Now,
That looks better.
the integral one?
Yeah.
Yeah, it looks better until you have to solve it. If you can solve it this way, this is mathematically going to be easier. But we will have some that you can only solve this way. Okay, and the difference is if the object has little clumps of mass, it's a lumpy mass, where it has a lump of mass here and a lump of mass here and a lump of mass here, and the rest of the object is essentially massless, then you can use this one. Because you can locate individual lumps of mass by their location. Okay? If it's a lumpy mass, you can use this. If it's a continuous mass distribution, this is the one we use. All right? Okay, so here we go. Here. here's A. I've got mass here and mass here. And the distance between these two is 2L. Okay? And I'm going to rotate it about this axis right here. So I'm going to spin it like this. Right about this spot. So here's A. Actually, you know what? We should do this. I think that's the math. Here's A. Number A. Here's number B.
I wonder what number that is.
Yes, of course. Here's number C. These are not necessarily drawn to scale. All right, here is number D. Oops. And here is number E. All right. Now, each one of these is like a barbell arrangement. Okay? Barbell, length 2L, mass M on each side. Barbell, mass M on each side, but only length L in between. Barbell with really long, 4L in between. By the way, this connecting rod in between is massless to make life simple. This is a half barbell, or a hammer, if you're in the Olympics. 2M, length L. And this one is an M and an M with a length L. Okay, which one has the largest moment of inertia? Or rank them in order of moment of inertia from high to low about this rotational axis. So they're going to be rotating like this around. So like this. Around that dashed axis. Go.
From the point at which they spin, right?
The radius will be from the pivot point from here to here.
Okay.
So we're going to use this one, right? Because we have a lumpy mass arrangement, right?
Yes.
Okay. So we're going to start from here to here. So the radius here would be L, right?
Yes.
Okay. So for our first one right here, the sum of my MR squareds. I have a M at a radius of L squared here, and I have a mass here, M, at a radius of L squared. So I get 2ML squared. There you go.
Well.
Have you ranked them in order yet? What's your order? C? Whoa, I got A, D, and E all the
I
same?
think D and A are the same.
A and D are the same?
Yes.
A and D, then what?
And then E. Yeah. And then B.
That's it? All right, look at this one. This one's pretty easy to calculate. There's just one mass. It's just 2ML squared, right?
Yeah.
Okay, look at this one right here. There's two masses. But this one is ML squared for this mass, and it's plus M0 squared. So it's just ML squared, right?
Yes.
Okay, and this one would be,
I have a question really fast.
yes.
Why on A is it just L and not 2L? And then for here you have L and no like L.
Ah, the pivot point is it's rotating about this point. So this R is from the radius from the rotational point. Okay? Does that help out?
Yes.
Okay. So this one here is this plus ML over 2 squared. So what is that?
1/2.
1/2 ML squared. And this one by far will be the greatest, right?
8 L's.
Is it 8L squared?
Yes.
Not ML squared.
Is he doing an example?
All right, does that look right?
Yes. Oh, I see.
Okay, now which ones of these are in free rotation? Which ones of these are in free rotation? About their own center of mass.
A, B,
Okay, this one, and this one. These could be things that are in space floating around, or you just toss through the air, right?
Yes.
Okay, now these, on the other hand, must have had something restraining their motion, right? Yeah, like they were hooked onto some sort of axis or something, right? Same thing here. Okay, there must be some sort of axis through this one that it's rotating about. Okay, restraining it here. Because it will not rotate that way by itself. Okay? So, everybody, we're going to have some that are in free rotation about their own center of mass and some that won't be. You just need to look to see where the actual pivot point in the problem is. Yeah?
For the sake of our homework, what do we do if the little bar part has mass?
What do we do if the bar part has mass? Good point. Thank you for asking. So let's say like this very first one. Let's say it has a bar that has mass. And so here its center of mass is right here. And say it has a mass of M.
Can we give an example with B?
It's supposed to go already over.
B, this one?
No, D as in dog.
Okay, first let's do this one.
No.
Will this mass of the bar make any difference?
No.
Okay, not, yeah. Okay.
M over 2 over A.
All right, here's the deal on this one, is that the center of mass is right here, but that would be like saying, look, my center of mass is right here somewhere, right? And if I rotate like this, or rotate like this, my center of mass is in the same spot, right? Right here. But, you're telling me if I rotate like this or rotate like this, is my moment of inertia the same?
So for that
No.
one, use the integral?
Okay, so what we need to do is if we have something like this, where you have a continuous mass distribution, right here, then you're going to need to use the integral.
Yay.
Okay, so like this one, is there a problem like this, where there's a continuous bar and then there's like some lump of mass on the end?
Yeah.
All right, we're going to have to use a continuous mass distribution. So we're going to have to use this, which we're going to talk about in a minute.
What if we already know it's moment of inertia?
Then you use the parallel axis theorem.
Oh, okay. Oh, okay.
Of course.
Of course.
How did we forget about that?
Oh no, he erased it.
How could you be so stupid? The parallel axis theorem, everyone.
The red one is working.
People who are watching the video.
Okay. We will talk about the parallel axis theorem in a minute, or 12, or more. Okay, let's say we have a hoop.
What? Oh, who?
A hoop, like a,
Oh,
Ring.
Yeah, let's do this.
Oh, Mr.
like a hoop.
I heard him say who.
Does it have spokes?
Here, even better. Yes, here you go. You see this? Like a hoop. Where's most of all of its mass?
Oh, yeah.
On the middle? What the heck? There's a bunch of wires in there. Right here. Okay?
Right?
Okay, like a hoop. A hoop.
Guys, that's my earring.
Like a, I think I said a hoof? No, hoop.
Dr. Seuss who?
Not a who. Horton, here's the hoop.
I love that movie. Where can you like
All right, a hoop. All right, and if it's rotated, where's its center of mass? Right there. Right where my eye is, right there. Okay. Now, if I rotate that thing like this, don't drop it.
You're gonna break your.
Break my what? Okay, if it's rotating about this point, you can see my nice axis there. All right? It's 3D, you couldn't tell.
Okay.
All right? Or a disc, here, disc, as opposed to a hoop.
This looks like somebody's hair.
Don't quit your day job.
Is it worse than before?
Mr. Bruins, what is that?
Or a solid sphere,
Are you in the shade now?
or a hollow sphere.
It's a hollow.
Okay? All right, so hoop. Okay, hoop. Hoop. Disc. Solid sphere. Or hollow sphere.
Oh, this one's on the.
This one is parallel.
Okay. Okay, so disc like this.
Like,
That's right. Hockey puck.
we should play hockey outside.
Hockey. Greatest spectator sport known to mankind.
Because you get to fight people.
That's right. It's the one where you get to watch it and watch people beat each other up. There's lots of physics in action. All right.
You should go to a hockey game.
All right. Or ring or hoop. Okay. Ring of mass or hoop of mass. Disc of mass. A solid sphere. See?
Ben's head.
Solid sphere. Or
Salvador's head.
wow. Or a hollow sphere.
No, I was gonna say Andy's head, but
Yeah, okay, Andy, come up here. I need a hollow sphere.
that was good.
Golly.
And like you said, all
Salvador. Salvador. Okay, that's right. Now, I got this question. If they're all the same mass m and they all have the same radius r, then which one has the highest moment of inertia? List them in order from high to low. Now, a hollow sphere, think of like a basketball. It's like a basketball, it's like a marble, bowling ball.
What is a solid sphere have?
Solid sphere has the first.
Okay, which one has the most, which one has the least? Put them in order.
Go high to low.
High to low, moment of inertia. Now remember, moment of inertia, just think of it this way. I equals the sum of the mr squared at this point. They all have the same mass, they all have the same r, but they won't all be the same.
Wait, they don't.
Which one has the highest moment of inertia?
We don't know.
I think the hoop.
The hoop. Solid.
Just because I'm guessing.
Who has the most? In fact, look everyone, if you just draw it two-dimensional so it's a little bit easier, it has a mass of m, and where is all of its mass at?
Oh, on the outside.
R. All of it's at r. So it has a moment of inertia of mr squared.
But isn't that the same for the sphere?
Yeah. No, it's effective
hollow sphere?
radius.
No.
Yeah, but the hollow sphere
It's got more R.
has
Less.
only this mass is exactly at r.
But isn't it?
Oh, it's
No, but
No,
it's.
it's effective
But it's the
radius.
same, but then it has more.
Because this
Because it
mass
has
up
mass
here,
zero,
the mass at the
here
top
has
and the
zero,
bottom,
here.
is at the
Oh, well, yeah.
rotational axis.
The total mass is broken
So
up.
if you plug this
They
in.
don't have
The
same-
total mass is broken up around the shell.
same mass.
So we say that
Oh,
that's
he
the
said they
same.
have the same arm.
No,
I'm
that
Okay, so my question is which one has the most mass near the rotational axis?
Okay.
Here.
The hollow
Solid
sphere.
The solid.
Solid.
One of the spheres.
Okay, this one's got mass along here, right?
Yeah.
This one's got mass all along here, right?
Yeah.
This one's the least.
That makes sense.
Wait,
Yeah.
what?
This one has the least moment of inertia.
I don't understand.
Because
I don't like this. 4K, 4K.
Oh shoot, what is it? It's 2/5. 2/5?
yeah, so if you have a sphere.
Been a year
and
since
I
I've done
have
these. I don't
my
remember
up and
what
down,
they
let's
are.
say up and down
Okay.
is my axis.
This one.
My R.
Excuse
my
me.
maximum is R.
Oh no. We'll calculate this a little bit. Actually, you know what? We will not calculate this one or this one. This is a three-dimensional
So where's-
integral.
So
No.
my moment of inertia can't all be mr squared. It has to be m like 0.1111 r squared. Or,
So where's the toothpaste coming
that's like an
All right.
integral
Now,
function.
from? Okay, so,
Radius.
okay.
okay, everyone.
I'll look at my teacher.
It will help if you know these. Memorize them. A lot of you are saying, well, where did these come from? Okay, do y'all see where this one comes from?
Yes.
Okay, that one's easy. Do y'all see that the rest of these cannot be mr squared? Do you at least see that?
Yeah.
Why?
Because this little piece of mass right here is not at r.
Oh, yeah.
But this little piece of mass out here is at r, right?
Okay, so do
And
that.
some of the mass is right here at the rotational axis, so its r is 0. So not all of the mass is providing rotational inertia.
So
Okay, so what about
how
that?
did you come up
Okay.
with 1/2?
How did I come up with 1/2? We'll actually calculate this one, I believe, yes. These two we will not calculate. All of these will require an integral to calculate, okay? I'm just showing you the answers to show you that they're different because of where the mass is distributed. Even if they all have the same mass and all the same radius, r and m, they don't have the same moment of inertia. Now, do you see that this one has a higher moment of inertia than this one? Because this is a hollow sphere, and notice there is only a little chunk of mass here and a little chunk of mass here, but the rest of the mass is all along the ridge, the outside radius, right?
So the more mass you have along
The more mass you have farther out, the higher the moment of inertia. The more mass you have in along the rotational axis, the lower the moment of inertia. Does that help, Megan?
Yeah.
Okay. Where this one has a whole bunch of mass in here.
Mr. Red, I showed you a question.
What's that? Oh, I'm sorry. Yes. What did I say? Oh, the more mass you have with a large radius, the higher the moment of inertia. The more mass you have along the rotational axis, then the less moment of inertia it has. Okay? Like for instance, which way could you rotate me? Stick a spear through me and rotate me, and I would have the largest moment of inertia possible.
Like
If your arms are
the axis
You know, if I'm standing like this,
through your middle horizontal.
yeah, you stick one like right through my belly button, and then rotate me like this way, right? My head and my feet would be as far away from the rotational axis as possible, right?
Yes.
Okay, how could you do the same thing if I'm standing like this and get the least moment of inertia? So you right through my head, straight down, and rotate me like you're roasting a pig, right?
I think you died.
All right. Okay, with this in theory, it's talking physics here.
It's all for physics.
All right, it's all for physics. You'd have the least moment of inertia. Does that make sense?
So we don't get to do a lab like that?
Yes, right. Here's the spear. Take your lab partner.
I know
Dude, I
what
think like
If I'm doing an experiment,
scientists
I'm
will take their friends on the wall and see how long they stay.
Where would you have to stick the thing from
what's that for?
It's from Winston Scientists. One of the blue categories.
Okay,
Take them on the wall.
let's get a little practice at this. Some more practice.
So can we look at how to calculate?
We will in just a minute. Okay, we're going to take this in a... What you just saw was the ending point of where we kind of want to be. It takes any kind of random shape and figure out the moment of inertia for it. But before we get there, we're going to start off with this equation and figure out how to find the moment of inertia for masses that are lumpy, that have discrete pieces of mass. So here you go. M, and M, 1 meter, 2 meters. All right, so here's your rotational axis. Here's axis A. Here's axis B. Here's axis C. And here's axis D. All right, rotating about axis A, B, C, and D, find the moment of inertia.
Oh, it's 1 meter.
The sum of the MR squareds. About axis A, how many masses do we have to worry about? We have 4, and they're all the same, so it's going to be nice and easy. So about A, it's just going to be 4 times M. What's the radius?
1.
So it's 1 meter, whoops, sorry, squared, times 4, right? Which is 4M,
And it's times
4M,
Oh, okay. I was like,
right? I didn't tell you what M was.
Kilogram meters squared or something.
Yes, and don't forget our units are kilogram meter squared. Okay? So our answer is 4M. What about for B? What is it?
Got 8.
How many masses make any difference?
1 meter squared. 2.
Hey, come on. How many masses make any difference? 2. So the sum of the mr squareds is going to be 2, because the two are the same. But these two masses have 0 radius. So they don't do anything.
2 and 4. I got 2 and 4.
So I get 2m, and then I get 2 squared, right?
So 2 and 4.
2m.
No.
8. You don't do math. Just put a diagonal line.
Hey, what the heck happened there?
2
Wow.
times 2 times 2.
That was mathematics.
That was funny.
Math magic. Oh, that's my new subject.
All right, here you go.
I should
What's
make
it
a
about
major on
C?
that.
M. 4
Yeah, I
m
got it.
times 1/2.
Okay, there's 4 of these. M times
1/2 squared.
1/2.
Then
squared.
a miracle happens.
So what's it going to be? M. About axis D, it's going to be 2m1 squared, which is just 2m, right?
Yes.
2.
All right, now look at the problem. Look at the diagram. Does that make sense that they're in that order? That about axis B you would have the largest moment of inertia, and about axis C you would have the least. Does that make sense?
Yes.
I think so.
Yeah. Yeah.
See, but number 4 is so much more
What
difficult
about at
than
point
this.
A, like where?
Problem 4 in your e-homework. I got it. Okay, problem 4. All right. A lot of you are saying, but wait a minute, this is way too easy. All right, what if I put the axis right here?
Well.
It'll be like this.
And let's say it rotates about, I don't know, the z-axis perhaps.
That'd be ugly.
A plus C.
Like this.
That you throw the thing, right?
Isn't it inertial?
Throw it.
Yes, like I took this and I threw it like, here, like this.
Like a spiral.
Like this, there's a mass here, mass here, mass here, mass here, and I'm taking it and I'm throwing it like this, or like this. So it's rotating like this, about this axis. Does that make sense?
Yeah.
All right, so it's a three-dimensional problem if you're looking at it that way. So here we go, about this axis. Moment of inertia about its center of mass rotating that way. Okay? How many masses? 4? Are all the masses the same distance away?
No.
Are they?
Yes.
Yes.
Yeah, they are. Here's the radius, r.
Is it?
R, and R. Okay? So I can just say 4 of these. Mass m. What's the radius?
Square root of 5 over
Square root of 5, right?
2 over 2.
Should just be square root of 5.
Should be square root of 5. A squared.
Which is 1/2.
A.
That's 1/2.
Oh, rats. 1/2.
And 1.
Rat.
1.
1/2 and 1.
So
1
it's
plus
square root of
1
5 over
fourth.
2.
Square
root of
5 over 2.
So 1/2 squared plus 1 squared square root.
Square root of 5 over 2. So
What is it?
5 over 2.
5 over 2.
5.
Square root of 5.
Yeah.
Squared, right?
What? So,
Because you square it.
Yes.
just for fun.
we did that. Yeah.
I know, you people, you do square root of 5 over 2 for fun. I would have left it as,
Square root of 5 over 4, then you
Square
would
root
forget
of
about square root of
1.25.
4. It looks better like square root of 5 over 2.
yeah, but, okay. But the thing is you're going to square the darn thing anyway. So you're going to be left with
You just get this.
4m, and then this is going to be 5/4. 4 goes away, you're left with 5m.
And just the masses are all the same, right?
That's only because all the masses are the same. Now is yours, the mass is the same?
No.
No, they're all different.
No.
Ah, then you will do this 4 different times for each individual mass, right?
That's not pretty.
In your problem,
Why would you do that to us?
In my problem, I have 3 of them the same and 1 different.
I have 2 the same and then 2 are.
Okay. Well, if the bar in the middle has mass, the answer is we haven't gotten there yet. Because it has a continuous mass, and so we have to use the integral. Okay? All right.
We do.
Now, you could do this for any axis they pick. Like, for instance, everyone, shh, what if they did this? What if they picked a different axis? What if they picked this axis right here?
Then they'd be really mean.
If I pick this axis right here, notice so far we have M, 2M, 4M, 5M, this was almost the highest, and this one, which is 8M, which is the highest. If I go and put my axis right here, so it's rotating about an axis like this, in the z-axis, where does it rank in there?
It's going to be the highest.
Why will it be the
Because
highest?
it has the longest radius.
Because it's got a really long radius. Now, one of the masses disappear, but you have this one with a radius that's squared, that's really long. So this is going to give you your highest moment of inertia of any spot, any axis on the object. Okay? There you go. All right. Okay, that was really nice. That was not so bad. It just takes a little bit of math. No big deal. But what if we have an object that has continuous mass? Okay, so here we go. Here's our first one. Okay?
So that's a solid.
Okay, so this is a ring of mass. A ring of mass or a hoop. Okay? If you have a ring of mass or a hoop, okay, we'll start off with the easiest one. Moment of inertia about the z-axis, because here's my x-axis, here's my y-axis, here's my z-axis, so we're talking about the z-axis. Alright? I have a continuous distribution of mass. So, integral r squared dm. Now, let's use our calculus knowledge. This is a radius of r. Where's the mass located? All at r, right? So for us, this becomes a constant. Right? Sorry, squared. Man, I'm just messing up today. The variable, little r, is always big R. It's always a constant. And by the way, just as a general rule of thumb in these kinds of integrations, generally what we do is the small symbol or the small variable is a variable. The small symbol is a variable, but a large uppercase letter is a constant. Okay? So when you see big R, that generally means a specific radius. Okay? A small r would mean any random radius. Okay, and what does this become then? So you got mr squared. So there you go. For our ring of mass, or hoop, the moment of inertia is just mr squared, which we already know. So let's do something a little more challenging. What if we have one like this? That is like a cylinder of mass.
And it's not hollow.
And it's not hollow. And I want to find the moment of inertia about the z-axis. Okay? So let's set up our integration. And we're going to rotate like this then, about the z-axis. That's the direction we're going to be rotating it about. So we need to know the moment of inertia about that. So here we go. Moment of inertia about the z-axis for our cylinder is integral r squared dm. Okay, now what we need to do then is what, well, let me ask you. Alright, it says that I have to sum up all of my masses and their appropriate radiuses squared, right? Do you see that as I move through the mass, I'm going to be changing radius? That this little piece of mass here has a certain radius, and this little piece of mass here has a certain radius, and so forth and so on, right? So as I move and sum up all my masses, each one has its own radius. So when I'm moving through my mass, I'm moving through space, right? I'm moving through three-dimensional space. Actually, ours is going to be a two-dimensional. Okay? So I need to have some way of relating. I need to relate space, R, and mass, M. Does anybody have a way to do that?
Mass over area.
Okay, a mass over area or a mass over a volume, which is a density. Actually, we're going to end up with, you can end up and define three different types of densities. Okay? Here's the density you're used to seeing. This is called volume density. Volume density is mass over volume. There's area density. For a two-dimensional object, you can define a sigma, which is mass over area. Or you can have a linear density.
Mass over area.
Which is a lambda, which is mass over length.
That's the rope one, right?
Yes, and so like for instance, we will use linear density to define the density like of wire or ropes or even a chain if it's long enough, where the individual links don't really make any difference. So linear density is convenient if you have a one-dimensional object. Like if you had a really long piece of wood or something, even though this has a rectangular shape, it's very long compared to its other dimensions. So you could approximate this as a one-dimensional object. Okay? But like a string or a rope or a wire, it works really well. And area density we can use if it's essentially a two-dimensional object. All right? We could define an area density for this one if we wanted to. All right? And we could solve this. Or we can do it with a volume density. Okay? We cannot use a linear density on this one because the axis about which we're rotating it is along the line of symmetry. And so it won't do us any good to do a linear density because we're rotating it about that axis where we would be calculating our density. Okay? So let's do a volume density because this is a good place to start. If you want to see an area density, we can define, if we have time at the end, we can try to define one. All right? So here's the deal. Volume densities. We have to know whether the density of the object is remaining constant or not. Okay? If the volume of the object is not remaining constant, this becomes a more complicated calculus problem. Okay? Which can be done. You just need to know what the equation is, the formula for the density. Now we'll run into those types of problems when we get into electricity, when we get into static electricity. We'll end up with problems where the charge distribution is not linear or uniform throughout. Okay? Like there's more charge around the outside than on the inside. Or vice versa. Or something weird like that. So here we go. So if we assume that in this particular object that our density is uniform throughout, we have this equation right here, but we can also do this. That means for every little dm, there is a little d volume associated with it. And every little bit of mass divided by its appropriate little piece of volume should come up with the same ratio of density rho. Does that make sense? If I take any little hunk out of this object, if I take a little piece out right here, take its little dm, divide by its little dv, it should equal rho. Does that make sense?
I guess.
Since it's continuous density.
Look, if I take this object right here, okay, it has a volume, It's made up of a certain number and type of atoms, right? If I take its volume, take its mass, divide by its volume, I have a density. If I take a chunk of it off and take that volume and its mass and find density, it should be the exact same number as this one, right?
Yes.
Because it's uniform.
Because it's uniform.
Yes.
Because it's
But that's not always true.
That's not always true. In most cases, we hope that's true because it makes the math simpler. But there are lots of objects where that's not true. For an object that is not uniform throughout. Okay? All right, so here we go. That means that if this is true, that means rho equals dm over dv. So what's dm? Rho dv. And I can take that and plug it in here. So this is your first main idea. That dm equals rho dv. This is calculus all over again. Okay? So our moment of inertia about the z-axis becomes integral r squared rho dv. But rho is a constant, we said, right?
Yes.
Now, if rho is not a constant, if rho is a function, say like a radius, then we would leave that function in here. Does that make sense? Like if there was a density that was rho equals 1 plus r squared. If that was our equation for density, then we would take that and we would plug it in here for rho. But we're assuming rho is constant, that our density is uniform throughout. So if that's the case, then rho comes out of the equation, and we get rho integral r squared dv. Now as we move through volume, we got to relate volume to radius, but that's a little bit easier.
Right.
You remember how you did that in calculus? Anyone remember? Anyone?
Volume to
For a cylinder.
Pi r squared times volume.
for the
Or
cylinder.
volume or something, right?
2 pi r squared
Times
right?
h. Or times length of
I
the.
know it's been like 3 years.
Right?
Been 2 years.
Yes, it has been 2 years for all of you. So let's go back.
It's the equation of the.
And let's do you remember the shell method?
Yes, I do.
And some of you go, oh, as in oh, or oh, as in oh. And some of you go, no. Okay, here's how this works. We're going to cut this into
Non-existent parts.
Excuse me? Eyeball.
Who said eyeball?
Hard.
Why is
all right, now, everyone, what we're going to do is this is our little differential volume right here. This is my dV, my little bitty piece of volume.
You cut out a reason from it all the way through?
And what we're going to do is we're going to integrate from here all the way out.
It's like a
We're
half.
going to start with a little ring of mass that goes all the way through, and then we're going to integrate all the way out. That's our differential volume.
No thing.
This is not the only way to do this. This is just the way I'm doing it. All right, so here, I'm going to take this little differential piece of volume out here like this. Here's my little differential piece of volume.
differential piece of volume?
That's what it's called. I'm going to take a little knife right here and I'm going to slice it. I'm going to spread the thing out. And so it's going to look like this.
It's like a frog.
Oh, how did I do that?
All right, here you go. If the length of this thing here is L, then the length of this thing here is L. If from here to here, what do we call that? Circumference. How do we calculate circumference? 2 pi r from here to here. Now is that 2 pi r or 2 pi r, big R? Hey, it's going to be changing because we're going to integrate from here outward, right?
Yes.
Oh, integral.
So it's going to be little r. And everyone, what's this? Oops, sorry.
R. Right?
This little thickness here.
Is it dv?
That's not my dv because this whole thing is my dv. That's my little dr.
Doctor.
lowercase.
Yeah. You remember this now, right, from calculus? Of course you do.
Of course, you can just write it down. I can remember.
So, my differential piece of volume is actually going to be a
Why couldn't you?
length times width times height.
Question.
Answer.
Is the other way you could do it is find the volume of the cylinder, then take the derivative of that to get dV, and then just
Yeah, how is
Go
that
through it.
different from what he just said?
I don't know. You can try it.
Because technically you would come out with the no, but the equation of it.
Oh.
The equation.
Yeah, he's right.
Will it work?
The volume of a cylinder is pi r squared L, right?
Yes.
And then
And
L
the
is
derivative
constant,
is
right?
2 pi r L dr.
Yes.
Oh, thank God, because I was like, I'm
This is all like related,
It's so easy, like
kind of.
Yeah.
pi r squared L.
It's just a derivative.
Ah, yeah.
Just do more self-talk.
So V is 2 pi r.
Squared.
Ah.
It's pi r squared L. Pi
Pi r squared L is the volume, area times length, right?
yeah.
Yes.
Okay, and then you take,
That's dV, and then that's
and that's 2 pi r
L.
drl. Yeah. Same thing.
Yes.
That'll work. Is that the way they taught you to do it in calculus? That'll work.
Derive it. Yes.
To use count.
All right, so I don't care how you get there. This is the way I was taught to do it, and if you got taught to do it that way, that's fine.
Well, you basically just explained why the derivative is. So it's still good.
All right,
It makes it a lot easier.
now here we go. Does that help some of you?
Yeah.
Yes.
Excellent.
I don't know.
See, a lot of times in math class they talk about it one way, and in physics class we talk about it a different way. But it's like the same thing. It's just with different language.
Yeah,
So
basically.
Tom is right.
we just got to make sure our language is matching up. Thanks for explaining that to me, because I don't know that I'm sure I've seen that before, but it's probably one of those things that it disappears from my mind, and I remember the one way that I was taught. Okay, here we go. L 2 pi r dr equals my dV. So I plug that in. Plug.
Okay.
And after I plug that in, it becomes, I get an L, I get a 2 pi, I get a rho out front. I get an integral, because this and this all goes out front. Oops, nope. Yeah, my rho stays up.
Yeah.
Constants.
Those are constant.
Yeah, 'cause they're all constants. Excellent. You wait long enough, they stop calling. So this goes in here, but that goes out front. So what I'm left inside with is a r squared
No,
r dr.
R
R
cubed.
cubed dr.
R cubed dr then, right? Now, what was the whole stinking point of going from dm to dv? Okay, the point of going from dm to dv was that when we moved through our little dm's, we were moving through space. And so therefore, as m moved, as we integrated through m, it varied with r, right?
Yes.
They were related. So we had to relate them. The way we relate them is through the concept of density. And then once we get density up here, we have rho and we have dv, but dv and r are related. So we have to get that dv into terms of dr. Okay? So we end up with this. So what the heck is this?
As you move through as your radius changes.
Well, can't you just do the integral of r cubed dr?
Why don't we just integrate that dude? Because we can integrate it now, right?
Yeah. 1/4 r to the fourth.
1/4?
Yes.
1/4 r to the
Fourth.
4th.
Plus.
Okay, where are we integrating from?
Oh. 0 to
0
big
to
R.
R. 0 to
R.
big R. 0 to R. So what does that become? 2 pi. I got an L. I got a rho. I got a 1/4. So put my 4 down here, and I got an R to the 4th.
Minus.
Which gives me
Yeah.
minus 0, right?
Yeah.
This gives me a
Moment of inertia.
1/2, right?
Wow.
Oh, wait.
Yay! Yeah. And that's our moment of inertia.
Now, I hate that. That looks horrible for moment of
And
inertia.
that's only if it's
I like
solid
it.
and constant.
It's
So let's do a little fancy footwork here.
No, you're not.
Fancy, yes. Yes. And don't argue with me.
Like you.
Rho is M3. Rho is
Yes. What is rho? Rho is m over v. Okay, what's m? M. What's v? V for a
2 pi, or pi r squared.
pi r squared times L. Okay, so I'm running out of room. I'm going to go over here.
Yeah, it all goes away. And it gives you.
And I'm going to end up with my moment of inertia z equals 1/2 pi L r squared, I'm sorry, r to the 4th, sorry. And my rho is equal to mass over pi r squared L. What does that become?
Wait, what did you? Oh, okay, I see. It becomes.
Okay, what did I do? I didn't like the fact that the length, that I had rho and length in here, and so what I did is I wanted to get rid of this rho, the density. And so what I did is I just plugged in what is density. Density is mass over volume.
Oh, and then you can
1/2
cancel
m r
out.
squared.
Yes, and my pi goes away,
Duh.
my L goes away,
Duh.
two of these r's goes away, and I'm left with 1/2 m r squared. Ta-da!
What the?
I don't care how you did that.
Let's stop.
My
Oh,
brain
and so that disc
continues.
is a cylinder.
There you go. All right, so here we go.
So, radius, the length is.
What did we just do? We just figured out what I'd already showed you, is that for a disk of any length along the z-axis, a cylinder,
We'll have the same.
will have the exact same moment of inertia. Sweet. So however long this thing is, however long this turns out to be, Dusty, ooh,
It's
messing up the moment of inertia.
Christmas and
All right, so however skinny or long this cylinder shape is, this disc, you'll get the same moment of inertia. M, the mass of it, r squared divided by 2. Sorry.
So is that how?
I'm sorry. Oh. Oh.
For Alexandria.
Okay.
But we're never going to have to like drive that
I
ourselves.
need 1/5.
Well, we hope not.
Last year's AP, not going to say never.
Yes, I'll never say never. You need to memorize these unless you want to derive them. Okay? These will not be on your test. So you need to memorize these. Okay, for a solid sphere, what did we say it was? 2/5 m r squared. And for a hollow is 2/3 m r squared. Now, we are not going to count, we just calculated the top two. We are not going to calculate the bottom two because they are three-dimensional shapes. So unless you want to do a three-dimensional integral,
Let's do it.
Yes.
Oh, Mr. Bruin, could you
Yes.
help us then with number 7? Because I don't understand the picture.
number 7.
Yeah.
Okay, there's still quite a bit we have to cover yet. We're running short on time, so let's get moving. Number 7.
The diagram.
Number 7. We can't talk about that yet.
Okay.
We need to get moving.
Okay, no more questions.
Okay, quiet. Okay, what if we have a uniform object like this, a uniform bar? Okay, like a meter stick. Okay, this meter stick is essentially one-dimensional. All right? Uniform bar. Okay, so let's start our integration. We're going to find the moment of inertia about the end. Okay, rotating like this, like a baseball bat. Okay? R squared dm integral. Okay, once again, as we move through our little differential mass. We're moving through space, right? Our differential mass in this case is easier to spot. It's right here. There's our little differential mass. Right there. It's little DM. Little bitty DM. Isn't that cute?
You have to say it with a high pitched voice.
And as we move through our DMs, we're changing radius, right? So therefore, we must come up with a way to relate the mass and the radius. So we're going to do that by density again. Now, you want to do that by volume density or linear density?
Linear.
Linear?
Yes.
All right. Well, let's see if we can get that one right. Linear density, lambda, is equal to mass over length.
Little r.
Or big R?
Or for us, actually mass over length. Okay? That's what it really means. Now for us, when we take the little differential mass, that's going to be over dr for us, right?
Yes.
Does that make sense?
Yeah.
So that becomes integral from 0 to the length of our object. Right? We're going to integrate from here to the actual length of the object.
Okay.
R squared. Okay, now wait a minute. What's dm then?
DR.
Lambda dr.
Lambda dr. So we get lambda dr. Now lambda is a constant, right? That becomes lambda out front, and when we integrate that, we get what?
1/3.
R.
Like that?
Yeah.
Okay, and we plug that in, we plug L in, and 0 gives us nothing, so we end up with lambda L cubed over 3. Okay, now, we want to get rid of the lambda, take the lambda back out. And so if we want to take the lambda back out, then what we do is we just take this and plug this in. But for our device, its density is lambda, its mass is m, but its actual length was
The whole length.
Big
big L, right? So therefore we take this, plug it back in, and when we do so, we get m over L, L third over 3. One of the L's goes away, leaving us with 1/3 mL squared. Voila! Bingo done. Okay, this is the moment of inertia for a uniform one-dimensional object, like a uniform bar or a rod, sometimes they call it.
Because basically this is just like
Lambda. I remember last time I was here, I couldn't remember how to write it. It's I made it like a wave. I did it like this, except for across and one. Couldn't remember.
Okay, now everyone, uniform 1D bar, where do we rotate it about?
The end.
Rotate it about the end. What if we rotate it about the center? Will we get the same number? No, we won't get the same number. We'll get a different number. And in fact, I'm not going to calculate it because we're running short on time. But for the center, like the center of mass of the object, it's 1/12 mL squared. Okay?
How do you define how big, like, the area is of your rotating axis?
How big the axis itself is?
Yeah, because if it's like huge and it includes the whole.
Now we, at this point, will be assuming that a rotating axis takes up no space.
No.
Right. Now you can get to the point where you can add that space in, because you'll add that space in as like a, essentially it'll be like a disc, right? It'll be a cylinder. So you'd add that little piece in, okay? All right, I think we have a problem in the e-homework about an object that is non-uniform.
What is the one?
Okay? And I think our object looks something like this, perhaps. Okay? So here's our object. Our object is like a triangular shape. All right?
Oh yeah, number 3. I was just
Number 3. And here's my equation for what this is. Y
The other one.
equals R, should be X,
Yeah, but
You should draw the other one.
over 2. Now, I'll draw it this way. Because otherwise, that'll be too easy on you.
What are you talking about?
Yeah, what are you talking about? All right. Okay, so here we go. Here's our integration. Moment of inertia is integral r squared dm. Okay?
Do we do area?
We could do area density. I solved it with volume density. Let's try it with area density, see if we end up with the same thing. All right, so here we go. Here's our little dm right here. Tiny bitsy dm. Okay? But our dm, actually we might be able to figure this out. I wonder if we can do this a different way. Let's try. Oh, we still need to use density though, don't we? So let's use area density this time. Let's try it since we had that suggestion. That's the area over, no, sorry, it's the mass over the area.
Yes.
Mass over the area. Our mass is dm over dA, right? But what's our little dA?
X times
Or the
or d
Really, it's going to be dx
dx times x by 2.
times y, right?
Yeah.
So our dm equals dx times y. But what's y?
X over 2.
X over 2. So you get x over 2 dx is our dm.
Or I thought that was our area.
Oh, sorry. Man, sorry. That's our area. Sorry.
You're forgiven.
I am, I hope. So what is our dm? Our dm is actually dA times our area density, right? So it's going to be this times this, right? So we have sigma x over 2 dx. Does that look good?
Yes.
So we plug that in right here. And now we're going to have to look at our equation right here. Our r in this case becomes x. We're going to integrate from 0 to, did I say what this was?
Yes.
X.
Here, let's make this length right here from 0 to L. How about that? This is out here.
Or how
And
about-
so we're going to integrate from 0 to L. Our r dimension is really going to be x dimension, right?
Okay.
Am I butchering calculus here?
Yes.
Excellent.
Very much.
Could be. So this is x squared dm, but we said that our dm is 0 to L. We got a sigma, we got an x squared, x over 2 dx. Okay, check me. Make sure my calculus isn't too bad. Are you my calculus monitor?
It's good.
Is it good?
Yeah, it's good.
Yeah.
We approve.
We approve of this message.
I was gonna say that.
Okay, so this becomes sigma over 2, integral 0 to L. I get x to the third dx. Does that look good?
Yes.
Yes.
Okay, integrate that. Sigma over 2, and I get x to the fourth over 4, 0 to L, right?
And L is X. Big X.
What's big X?
Right? L.
Oh, it's L. Well, you could do big X if you'd like. I just do an L, so that's the length of the object. So we get sigma L to the fourth over 8. Does that look good?
Yeah.
Oh, no.
What is sigma?
But area.
What is sigma, though?
Area? Yeah.
Sigma is
Mass over area,
One
right?
area.
So
doesn't it have to be area under the
sigma
curve?
is mass over area, but what's our area?
You
One
just
half x times x.
1/2
Isn't it
base
base
times height.
Yeah.
1/2.
base times height.
So
Base
it's
times
mass over 1/2 base times height. But what is our base?
X.
L.
Or L.
1/2 L. What's our height?
Y.
Or
L over
2.
2. Right here, right? Our length is L, and our height is L over 2. So what the heck? I'm running out of room here.
4m over L squared.
That's 4m over L squared.
Sweet.
Okay, so you plug that in right here, and you get 4m over L squared, L to the fourth over 8.
This announcement, I need to see the following people in the health office at this time. Natalie Amaya, Nefertiti Bill, Zulema Benavides, Miguel Benavides.
Aha!
Myron
That's what I got.
Barone, Anna Bruno, Eric Cassiano,
I
Kevin
approve of
Shaw,
this message.
I can do that even if the
Foxton,
triangle's the other
Alan
way around.
Garcia.
Yes, and you can do that even if the triangle's the other way around, right?
Brenda Johnson, Hector Miranda.
Actually, this should work for any, should it work for any triangle? Or should it only work for this triangle? Now be careful, you need to find out what your relationship is between X and Y, because this relationship will be different for yours than mine.
Fabian Vasquez, Raven, Watson Young, and Edison Ranger. I need to see these people immediately. Thank you.
You would integrate from, I think you would still integrate from 0 to L, but your triangle's opposite, so your equation will be different here. Like for instance, it might be a negative.
I can't see.
I
Yes.
put a big circle thing around that because I was forgetting.
Okay? That will change your moment of inertia. Yours will be different than mine, although the calculation technique will be similar. Okay, as we rock it through, we have two major things yet to do. In 8 minutes or less.
Okay, let's go.
Okay, here is the answer to question number 7. If you look at number 7, it says you have a solid sphere, but this crazy solid sphere is not rotating about the center of mass of the object, it's rotating about the rim of the sphere.
So in this one, would you have to take different discs?
So the rod is rotating around the sphere.
So instead of the sphere rotating about this axis, okay, where its center of mass is right here, we have it rotating about this axis. Okay, everyone, this is really important and an extremely useful and important tool. This is called the parallel axis theorem. Oh,
Parallel axis.
I hope you got a prize for coming up with this, mister.
it's called theorem.
T-H-E-O-R-E.
There you go. I had my O and my R backwards. I'm like, dude, that was horrible. Okay, here we go. Parallel axis theorem. Here's the deal. The parallel axis theorem says, if you know the moment of inertia about the object and the axis passes through its center of mass, then you can relate that mathematically to any other axis you want as long as that axis is parallel to the first axis. Okay?
Sweet.
So here it is. The moment of inertia about any axis, it has to be parallel to the moment of inertia about its center of mass. Now the moment of inertia, the axis here has to pass through its center of mass, and the axis here can be anywhere else, but it has to be parallel. So this axis through the center of mass and this axis anywhere else could be way out here. As long as they're parallel, all you have to do is add md squared, where d is the distance between the two parallel axes, and m is the mass of the object.
Oh, I see.
So it's 1/2 R.
So what is the moment of inertia for a sphere?
For sphere.
Solid sphere or hollow?
Solid.
Solid.
Right there. So this is the moment of inertia about its center of mass. Notice this is about the center of mass, this is about the center of mass, this is through the center of mass, this is through the center of mass. This one is not through the center of mass. This one is. Okay, so careful, this one is not.
And you can't do it.
So you can't use the parallel axis theorem for this one. Okay?
But
So you take your sphere in here, which is what?
It's
You can subtract.
Yeah. But
And what's our radius?
R.
R squared. So you take that, put it together, and I just answered number 7 for you.
Thank
You are
you.
so amazing.
Mr. Barron, just
Quick, did you write it down? Oh, it's gone.
I actually did that.
Bianca, turn around. You missed it. He already erased it.
we'll ask
How
that.
many rounds?
Okay.
Okay.
So wait, but I'm
Yeah, that's a
confused.
good question, right? 'Cause-
Seven
I
yeah,
think so.
yeah, it would be. See, 112.
Now, several of you are saying, wait a minute. But aren't these two related? And the answer is absolutely. Because look, here's our one-dimensional object.
So is that how they just do it?
Here's our center of mass.
And they're parallel.
And the moment of inertia here is 1/12 ml squared. Now, if I move the axis to here, and as long as they're parallel, the moment of inertia over here should be the moment of inertia here plus md squared, which should be 1/12 ml squared here plus m. Okay, this is 1/2 the length, right?
But it's 1/4.
1/2 squared, which is 1/4. So you get 1/12 ml squared plus 1/4 ml squared, which equals 1/3 ml squared. Voila! That's how you get that.
That was really fast writing. What else do we need to learn?
Okay, one last thing, because we have 3 minutes.
So Mr. Bruin, we can put our axis anywhere
No questions.
and solve it, and then just do the parallel to.
Yes. So what you do, and oh, one quick thing, everyone. The moment of inertia through the center of mass on any axis will give you the minimum moment of inertia. This is the minimum moment of inertia an object will have for that axis. Like the z-axis through the center of mass will be the minimum moment of inertia for the z-axis. If you rotate it about the x-axis through the center of mass, that will be the minimum moment of inertia for any kind of x-axis rotation. Does that make sense?
So why is it?
Wait, what?
It's minimum because you're at the center of the object and most of the mass is at the center with a radius of 0. So it'll always be the smallest about that axis.
So
Okay,
what's
so
the
the
biggest?
parallel axis thing, it doesn't matter where the parallel axis is.
Yes. So like if I have this object and I decide to rotate it about this point instead, as long as this axis and this axis are parallel, I can relate the two.
And D is just the
Distance between the axes.
okay.
Okay, so what if we have this thing?
How about
What if we have this wheel that has spokes like this? And you go, and I have to figure out the moment of inertia of this. Well, you know what? To me, that looks like the moment of inertia about this object plus the moment of inertia about this object plus the moment of inertia about this object. And I happen to know every one of those.
can you do it that way?
And I can add them all up. So this is the moment of inertia about this bar around the center. So I'll have a 1/12 mr squared, r because this is the radius, plus a 1/12, mr squared, plus a, what's this thing? Looks like a hoop to me. Plus an mr squared. Now notice, this is the mass of this bar, this is the mass of this bar, this is the mass of the hoop, right? The masses may not all be the same. But in my diagram, all the radiuses are the same, right? Okay, what if you have an object that looks like this? What if you have an object that's like this? And you rotate it about this axis, and you have a mass here. Okay, now look. Do I know the moment of inertia about this one? And I can use parallel axis to move it here.
Yes.
So that would be the moment of inertia of this object, right?
Yes.
So I'd have a moment of inertia about that bar plus an
And then you
ml
do the same thing for the sphere.
md squared. And then I can do the sphere and move it as well and add them together. Okay? These are scalars, and so you can add these components up.